Good day, everyone. I am Tomas Matiginas Jr. with my co-member Jerome Matugas. For now, we are going to discuss the deep well pump with a diagram and two sample problem. So first, what is deep well pump? A deep well pump is a sunken well bore extending more than 25 feet underground used to extract water. So, and we have here the electronic deep well pump diagram, which has a motor, centrifugal pump, impeller, return pipe, injector, nozzle, foot valve, screen, and well casing. And the two problem. Problem 1. A submersible multi-stage centrifugal deep well pump with 260 gallon per minute capacity is installed in well with 27 feet below the static water level. Drawn down when pumping a rated capacity is 10 feet. The pump delivers that water into 25 gallons capacity overhead storage tank. Total discharge head developed by pumping, including friction and piping, is 243 feet. Calculate the brake power required to drive the pump if pump efficiency is 70%. So this problem is required to calculate the brake power using the formula of brake power is equals to water power over the pump efficiency. So calculate the water water power. We have Q, or volume flow rate, is equals to 260 gallon per minute. So convert to feet cube per minute. We have 1 feet cube is equivalent to 7.48 gallon. So cancel the gallon. So volume flow rate is equals to 260 times 1 over 7.48. We have 34.76 feet cube per minute. So the total head, or H, is equals to 243 feet minus 27 feet minus 10 feet. So is equals to 243 feet minus 27 feet minus 10 feet is equals to 226 feet. So we can solve now the water power. So water power is equals to specific weight times volume flow rate times total head. So substitute constant of 62.4 pound per feet cube times 34.76 feet cube per minute times 226 feet. So cancel, we have 62.4 times 34.76 times 226. We have 49,199.424. So feet pound per minute. So convert this to HP. We have 1 HP is equals to 33,000 feet pound per minute. So divide 38,000. We have 14.85 HP water power. So using this formula to calculate the brake power, we have 14.85 HP over the pump efficiency, which is 70%, divides 0.70. We have 21.22 HP. So brake power. So we have the brake power. For problem number 2, water is in the rural areas if often extracted from underground water source whose free surface is 60 meter below ground level. The water is to be raised 5 meter above the ground by a pump. The diameter of the pipe is 10 cm at the inlet and 15 cm of the exit, neglecting any heat interaction with the surroundings and frictional heating effect. What is the necessary power input of the pump in kilowatt for a steady flow of water at the rate of 15 liter per second, assuming the pump efficiency of 74%. In the second problem, is required to determine the input power, which is input power is equals to water power over the pump efficiency. So, in other words, input power is equals to specific weight times volume flow rate times total head all over pump efficiency. So, where where volume flow rate is equals to 15 liter per second or 0.015 meter cube per second, and the specific weight is equals to 9.81 kilonewton meter cube. So to find the total head, we have the formula of total head is equals to specific sa velocity squared minus vs squared over 2 times g or acceleration due to the gravity plus z d minus cs or static head. So first find the velocity. We have the formula of vs or specific velocity is equals to volume flow rate over pi over 4 times the outer diameter squared. So substitute, we have 0.015 cubic meter per second over pi 4 times 0.10 meter squared. So we have 0.15 over pi over 4 times 0.10 squared is equals to 1.91 meter per second. 1.91 meter per second. So the VD is equals to Q, same as initial velocity, 1/4 times the inner diameter squared. Substitute 0.15 meter cube times 0.15 meter squared. So we have 0.85 meter per second. 0.85 meter per second. So we have now the velocity. So substitute, we have total head is equals to VD, which is 0.85 meter per second squared minus the specific velocity, which is 1.91 meter per second over 2 times acceleration due to the gravity, 9.81 meter per second squared, plus the static head, which is 5 meter minus negative 60 meter. So calculate using the scientific calculator. We have 0.85 squared minus 1.91 squared over 2 times 9.81 plus 5 minus negative 60. We have 64, the total head is 64.85. So let's proceed to the input power. So substitute, input power is equals to specific weight, which is 9.81 kilonewton meter cube times the volume flow rate, which is 0.015 meter cube per second times 64.85 all over the pump efficiency, which is 74% or 0.74. So calculate 9.81 times 0.015 times 64.85 all over 0.74. So we have input power of 12.896 kilowatts. So the answer is 12.896 kilowatts.